Hello everyone, this is Abhishek and I welcome all of you to this session. In this session, we'll talk about time series analysis and we'll discuss it through the case study and where we'll be using the air passenger data. This data is widely used and are available on various platforms. So I downloaded it from Kaggle. So in this section, we'll have a quick introduction or heads up about the dataset and our objective. So as I mentioned earlier, uh, I have downloaded data from Kaggle. The dataset contains number of air passengers who have availed flight as a mode of transportation from 1st of January 1949 to 1st of December 1960. So overall, there will be 144 data points, and our primary objective will be to forecast the number of passengers in the next 10 years. So now let us discuss the agendas for the day. Just I'll bring my pen on. Okay, so we'll start with by discussing the definition of time series, its concept, and its difference with simple linear regression. We'll follow that up by discussing the different types of models available in time series, that is additive and multiplicative. I will then try and understand the different components of time series, namely trend, seasonality, cyclicity. Okay, and then we'll try and discuss the concept of stationarity, its importance, definition, by which we can check whether a data set is stationary or not, and then the different processes through which you can transform the dataset from non-stationary to stationary. Okay, then we'll deep dive into the different predictive models. We'll discuss all these models one by one, and after that we'll try and understand the how to interpret the model summary. What are the different parameters and how they should be used? And then using those parameters, we'll choose our best model, and using that model, we'll be forecasting our next 10 periods, which is in this case the next 10 years. Okay, so moving ahead, we can see that we have imported the necessary libraries for our work. And apart from this, we'll be also using the stats models, which will be importing when we'll perform the ARIMA models. Okay. In this section, I have defined a couple of parameters, general parameters, which will be applicable to all the plots that we're gonna make. So this is optional. You can do that, or you can define them whenever you are plotting a graph. And then I have imported our data set, okay, and stored it in a data frame df. So in this section, we have used the info and describe command to understand the data set. So by using the info, we can see that there is only one column, that is passengers. It has got 144 data points and all of them are non-null, which means there are no missing values in the data set. Okay, and from the describe command, we can see that the average number of passengers who have availed this as a mode of transportation for this period is 280 with a standard deviation of almost 120, correct? But if you ask me about the business observation, I learned like to go with this mean because this is the overall mean for a period of 12 years. However, we have seen that this data has fluctuated. Okay, so in this case, I like to prefer to have a rolling mean or a moving average to determine average number of passengers who were availing flights as a mode of transportation during this period of time. So hi, in this section, we'll try and understand what is time series. As we all know, time series is a collection of data points which has been recorded over a period of time. Typical time series would be recorded or over an even interval of time, and these even intervals should be ordered chronologically for the easiness of our analysis. And the difference between time series and simple linear regression would be, in simple linear regression, there should be at least two variables, one target, another predictor. But in time series, as we have seen, there is only one variable, which has been recorded over a continuous period of time. So now we will see the two very important models in time series. One is additive, another is multiplicative model. So what is the difference between two? To explain that, I'd like to first say in any business, a certain factor or outcome is actually a combination of different factors which impacts it either in a combination of all of them or separately. So, based on this definition, and with respect to this case study, let us try and understand the difference between additive and multiplicative models. Say, in this example, we have three factors. First of all, we have seen that the number of passengers availing flight as a mode of transportation increased from 1949 to 1960. Now, this could have happened because of several factors. Say, one of them is the air travel became more and more safer over this period of time. Another could be air travel became more and more cheaper. And let us take another factor. Air travel has become more and more popular. So let us say there are only these three factors that have contributed towards this increment in the flight passengers. Okay. So in additive model, what it says is that these uh, factors should be independent of each other. Although they contribute together towards this growth, they will not impact each other individually. Okay. So to break it down, there would be a certain section of passenger who have started using flight because of the fact that the air travel has become safer. There would be another segment who have started using this flight as a mode of transportation because they think the air travel has become cheaper over the period of time would help them. And another segment of people will be there who have started using this flight as a mode of transportation because it has become more safer over the period of time. So individually they do not have any relation with each other, but however they have all started using flight as a mode of transportation, hence the number have increased or the demand has increased. Okay. In multiplicative model, uh, we can say all the three factors that we have discussed earlier are interrelated. Say over this period of time between 1949 to 1960, air travel became more safer, as a result of which more and more people have started using it, so the demand has gone up. So the airlines can now operate their fleets at a lower cost. Hence, the flight prices have gone down, and as a result of flights become more cheaper, more and more a number of people are recommending it. Hence, it is becoming more popular. So you can see all these three factors are in a way affecting each other. So that is the fundamental of multiplicative model, where it says these three factors will amplify each other or will impact each other, and together they will impact the business model or the business outcome. So that is the fundamental of additive models and multiplicative models. So the next obvious question is when to use which model. So this we'll have to decide by looking at the data set. However, in case of multiplicative model, what we will notice is that the magnitude of the seasonal movement will increase with the number of data points. But in additive model, both of this magnitude and the data number of data are independent of each other. So in case of a multiplicative model, what we can expect is we can expect somewhere as the number of data points increase, seasonality will also increase. But in case of additive, uh, number of data points has nothing to do with this what do you call nothing to do with this amplitude of the seasonal variation. Okay. So this is a basic layman term you can say, but we'll discuss about it more when we'll see the our visualization of the dataset. Okay. So as discussed earlier, we have plotted our dataset using matplotlib. Correct. So here we can see this is our data set when plotted against each other. Okay. So let us just take some time to understand the dataset. But before that, let me talk about the different components of time series. There are mainly three components of time series: trend, seasonality, and cyclicity. So trend is basically the upward or downward movement of the dataset overall, whereas seasonality is a repetitive, predictable pattern which can be observed over a period of time. And now this period of time should be less than a year. Okay. And cyclicity would be another repetitive pattern, but they are not distributed over a period of uh, any predicted period. Like they can occur once in 2 years or once in 1 year. So they are not like they are though they are pattern, they cannot be predicted like when they will occur. So these are basically the three components of a time series. Now let us quickly try and understand our data set. Okay, so in our data set we can see there exists a train component. The number of passengers have increased, right? From this point is 1949 and this is 1969, I guess, over here. So the overall number of passengers have increased. But if we talk about the individual period like 1949 to 1950, again 1950 to say 1951, as this goes by, we see a regular pattern. Like the year will start on a low note, it will go up, it will come down, and towards the end of the year, again it will fall drastically, and again it will repeat itself over this entire period of time. Only thing is that their amplitude is changing with the number of data. So this is a multiplicative model as discussed earlier. Again, on the basis of that, you can also see this pattern is repeating every year, correct? So since it is repeating every year, you can say there is a seasonal variation in this data set. As for the cyclicity, until and unless we will decompose this data, we will not understand whether there exists any pattern which is not repeating itself for a predictable period of time. So we'll see that when we'll decompose this data set. But as of now, we can clearly identify a trend, upward moving trend, and some seasonal variation, which we'll have to take care of. Okay. So in this section, we'll talk about stationarity. So what is stationarity? It's one of the most important criteria in time series analysis. Before performing any time series analysis, what we are required to do is to check whether our given data set is stationary or not. And if they are not stationary, we'll convert them to a stationary data set, and then only we can perform any predictive model on those data set. Okay. So what is stationary? A stationary, in a very simple term, would be any data set which have a approximately constant mean and variance. Both of them should be constant or approximately constant. Okay. So how to check whether a data set is stationary or not? We can do that by plotting the average or the rolling mean and standard deviation on the graph, or there is a statistical test we'll be using, that is ADF or augmented decuplier test. Okay, so let's see. In this step, what we have done is that we have taken our DF1, that is our data set, and we have performed rolling or moving average for a period of 12 months on it, and we have also found out a moving standard deviation for a period of 12 months, and we have stored them in moving average and moving standard deviation variable. So we'll quickly print that to see how the results are coming. So just a minute. So since we have taken a period of 12 months, so the first 11 data points should be null, and the average standard deviation should be started plotting from the 12th position. Correct. So that is what we are checking over here. Now, just a second, I'll just scroll down to the next part. Okay. So in this section, what we have done is that we have plotted the original data set, and on that we have plotted our where it is, we have plotted our actual data set, and on that we have plotted our average mean, moving average, and the standard deviation. So if we pay some closer attention to this plot, we could see that the mean, which is represented by moving average, which is represented by the red line, is not constant. Like it is starting from right around 110, and it is ending at around 450 or 60. So the range is very high. So that is not constant. And similarly, for the standard deviation, it is also starting at around say how much? It's 10, I guess. Okay, and the highest point is at almost around 50 to 60. So we could see both the moving average and the standard deviation, they are not constant. Okay, and this fact could be corroborated with a statistical test, that is the augmented decuplier or ADF test. Just a minute, I'll just clear these things. Okay, so in this section, we'll import the ADF decuplier test from the stats tools, and we'll perform the statistical test on our TF1. So you could see that after performing this decuplier test, we'll be testing this against our null hypothesis, that is the data set is not stationary. So, and our threshold value would be 0.05 or the p-value. I'll explain what is that. So as mentioned, our null hypothesis is data is not stationary. Okay, and our p-value, what we have observed, is 0.9 or 99%. Since our test value or our threshold value is 0.05, To establish the fact that this data is stationary or to reject the null hypothesis, we need to achieve a value which is lesser than 0.05. But in this case, our observed p-value is much higher than 0.05. So we can conclude that in this case, we have failed to reject null hypothesis. Hence, this data set is not stationary. Okay. Now the next obvious question is, what will happen when the data set is not stationary? We cannot perform anything, correct? So we'll have to transform this data set into a stationary one from a non-stationary one, correct? To do so, we have certain mechanism. We could follow any one of them. We could perform a log transformation on our data set. We could also find the moving average and then subtract this moving average from our actual data set. We could do the similar thing by finding the exponential moving average. And the most famous and the important procedure is this shift, whereby we take the lag from the previous value. Now we'll discuss that, and most of the time this works, and people try to use this very often. And the fifth will be the seasonal decomposition, whereby from the data set we will remove the trend component and the seasonal component. Those remaining residual will be we will try and find out whether that is stationary or not. So this is one of the way to do so. So in this section, we'll try out all this method one by one and see which method is resulting or giving us the stationary data set. Okay, so let's move on. So hi, in this section, we'll talk about the different ways in which we can transform our non-stationary data to a stationary one. So we'll be discussing these 5 processes one by one, and we'll see which one of them returns us the best stationary data set. And then we'll perform our time series models on this stationary data sets. Okay, so before we move ahead with our with these processes, let me just quickly take you through this custom function that I've created. So this function basically includes 2 things. One, it will involve a graph that will plot the moving average and the standard deviation of the transform dataset, and it will also include the result of the Dickey-Fuller test when we will apply this function on the transform datasets. So the first process that we'd like to talk about is log transformation. In this process, what we do is that we take our original dataset and we get its log variant, and then we'll store it in this df1 log data frame. And after that, we'll call our custom function that is test stationarity, and we'll pass this df1 log in. So once this is done, we'll see the results. Okay. So after log transformation, we could see that the number of passenger has been transformed from 4.75 to 6.50. That is its log variant, which was usually or otherwise was from 112 to 430. So the range is reduced drastically. So now let us see how the rolling average or the rolling mean and the rolling standard deviation works out. So here you can see that the average, the moving average is ranging somewhere between is like 4.75 to 6, which was our maximum result in the previous graph. Okay, and the standard deviation has also stabilized a lot. It is just like it's almost stabilized. You could see this from this trend. Okay, so now let us see the result of the Eddy-Fuller test. Okay, just a minute. Eddy-Fuller test. Correct. So in the Dickey-Fuller test, what we can see is that the p-value that we have got is 0.4, which is significantly larger than 0.05. Correct. So even though you could visually see that the rolling mean and the rolling standard deviation has almost stabilized, but the data set has not yet been transformed into a stationary one. Okay, so we'll go to our next step, or we'll try out some other processes to see whether we can stabilize this data or not. So in this process, we'll see how to do differencing using simple moving average. So it is basically a process where we'll find out the simple moving average of our log dataset, log transform dataset, and then we'll subtract it from its previous value. This is what we have done. We have found out the moving average for a period of 12. Okay, and then we have stored it into our df1 log moving average variable, and finally we have subtracted it from the log transform dataset, and then we have called our custom function. Let's see what the result comes after passing this different data set into this function. Yeah. So you can see that after differencing our moving average, which we have performed on our log transform data set, and when it was subtracted from its previous value, the range that is the number of passenger range has further decreased. So it is now ranging from minus 0.2 to 0.3. So like 2 and 3, 5 units that is ranging. So now let us see how the moving average and the variance of this data set is actually performing. So now we can see that the red line is the moving average and the green line is our rolling standard deviation. Okay, so it is also stabilized. It is like the moving average is ranging from like somewhat 0.01 to a maximum of 0.1, and our standard deviation has also stabilized. So let's see statistically how much stationary our data set has become after performing this moving average differentiation. Okay, so let me just scroll down again. Okay, so the result of the decuplier test, we can see that its p-value is 0.02, which is significantly lesser than 0.05. Thus, we have enough evidence to reject our null hypothesis and conclude that this data set, just a second, this dataset has become stationary. Okay, so for our further analysis, we could go ahead with this dataset only, but because of this session, we will also look at the remaining number of processes: exponential moving average, shifting. Then we'll also talk about seasonal decomposition in the later section. Okay, let me just quickly take you through this section. This is again like the previous section. We'll find the moving average and we'll differentiate it from its previous value. But in this case, we'll find the exponential moving average. Okay, we'll do the same thing. We'll find the exponential moving average. We'll store it in a variable and then we'll separate it from our log transform data set. Okay, over here. Fine. And finally, we'll call our custom function and we'll pass on this difference data set into this custom function and we'll check the results. So let us now quickly have a look at our result. So in this case, we can see the number of passenger has been transformed between a range of 4.75 to 6.50. And that's good. Let's almost like 1.25 and 1.75 of a range, 2525. Yeah. So now let us see the result of our Kiki Fuller test and our visualization. Okay. So over here we can see that both the rolling mean and the standard deviation has stabilized, as you can see. Now let us see the result of the decuplier test. Just a minute. We just get rid of this selection. Okay. So the result of decuplier test is like 0.05, which is again lesser than 0.05. Sorry, the p-value we have got from this transformation is 0.005, which is lesser than 0.05. Thus, we can conclude that in this case, we fail to accept the null hypothesis, and we can conclude that this data set, after transforming the log transform data set um, into a data set where we have subtracted the moving average, exponential moving average from its previous value, we have obtained a stationary data set. So you could go ahead with this model also, this data set also, but let us just take the other procedures ones. So in our fourth step, this is the most famous process of all. We call this as shifting. We subtract the present value from the previous value and we can do it in steps. So let us see how it works. So we'll just simply take our log transform data set and we'll do a shift of 1. This is by default 1. Okay, so we'll just take the next value and we'll subtract it from its previous value. Okay, and then we'll call our custom function and we'll just pass our uh, one shifted data set in this. So let us just quickly check the results. You can see that this thing, both the mean and the standard deviation have significantly stabilized. You can observe that over here, but we'll have to check it through the Tiki-Fuller test to actually find out the number. Okay, so let us see. Just a minute, I'll just remove these two things. Okay, so now from the Tiki-Fuller test, we can see that the p-value observed is 0.07, which is slightly higher than our threshold value of 0.05. So as we have discussed earlier, that we can go ahead with approximately stationary data set. So you can go ahead with this one, but already we have got two stationary data sets, that is one from moving average and one from exponential moving average. The choice is yours, but let us see whether we can convert this data set into a stationary one also. So to do so, what we can do is that we can take a shift of two steps. See, in order to make it stationary, we will try and shift the values two periods into the next step. Okay, so let us see what is the result of doing a shift of two. So you can see over here, unlike previous one, we have mentioned the shift of two here, and we have repeated the same step. So let us quickly find out the uh, result of the decubilant test. Yeah, so we can clearly see that now the dataset have become stabilized. Whereas it was earlier 0.07, now it has become 0.02. So we can now say that this dataset is stationary and we fail to accept our null hypothesis. Okay, and we can move ahead with this dataset, that is shift of two. Finally, let us talk about the last step, last process in which we can transform our dataset into a stationary one from a non-stationary one. Okay, so just a minute. Yeah, so in order to do so, the fundamental is that we'll break down our time series data into its components like trend, seasonality, and cyclicity. Okay, so when we'll take out these components from our data set, all will be remain is the residuals. Okay, so this residual is supposed to be stationary. Like, so we'll just try to find out the residual and we'll try and transfer that residual data set into our stationary function, custom function that we have already created. So let us see what happens when we do so. So in order to do a seasonal decomposition, we will call this function from our stats model and we'll decompose it into trend, seasonal, and residual. Okay. So after doing so, let us plot the decomposed data set now. So after plotting, this is what we have got. So as we were discussing in the earlier section, we could clearly see this is our original dataset. This is the trend that we are talking about in the dataset, that it has an upward moving trend, correct? This is the trend line, okay? And this is the seasonality. Seasonality, as we have defined earlier, it will be a pattern. It will be a repeated pattern, which we can predict over a period of time. Generally, that is less than a year or equal to an year. So when we take out these two things from this data set, original data set, what the remaining things we'll get is called the residuals. That is this part. So now we'll just pass this residual data set into our custom function. Okay, and we'll see what the result comes in the decubilant test. Correct. So let us just quickly do that. This is the plot again. So we'll just quickly refer to the decubilant test. Yeah. So you can see that it is significantly lesser than 0.05. Correct. So you can also conclude that using this process also we can get a stationary data set in this case. So to conclude, we have got a stationary data set by using a moving average, exponential moving average, shifting of second order, and seasonal decomposition. We can move ahead with any one of them. So let us see. In this case study, we'll just go ahead with one of the dataset, transform dataset in the latest section. So let us see that. Okay, before we move further ahead, I'd like to say one thing that in ARIMA model, we need to pass three parameters, P, T, Q. Okay, for autoregressive, MA, and differentiation. Okay, so in order to find out this P, Q, and T, P, T, Q order, we can either do it from plot or we have a function, a direct function in stats model called the select order, ARIMA select order. We can use that to find the order of AR and MA. Fine. So we'll do that using this tool, and I have passed in both the shifting dataset. Okay, since this is a popular method, we'll just go ahead with this one in this case study. You guys can try out the other stationary datasets also. So after running this order select on this two dataset, we can see that both the order of P and Q are same. So we can take any one of them and move ahead. Where D will be, we have kept it as 1, or you can take it as 2. Okay? As for your, is both the thing is applicable. D is 1 when our P value was 0.07, and when it was 2, it was 0.07. 2, correct? So let us first try with D and see what the result comes. And if it does not satisfy our need, we'll just go ahead with a properly stationary data set. Okay. So just let us just transform that. And so as we have defined earlier, in this case study, we'll have different models of time series to predict or to forecast the future. The first one will be the autoregressive. The second one will be the moving average. The third one will be the autoregressive and moving average model. Fourth one will be the ARIMA, and if needed, we'll go ahead with SARIMA also. So let's see. In order to do an autoregressive model, we just need to do one thing. In ARIMA model, we will make the MA part, moving average part, or the Q as 0. Okay. So the remaining thing will be autoregressive. So we have done that only. We have named it as model 1, and the result is stored in AR, results AR. Okay. So after doing that, we have call the result summary. Okay. So let us see the output of the result. Just a minute. Let me just quickly go through this scroll down. Okay. So this is the result. Let us take some time to understand the output. Okay. So yeah. So over here in the first section, in the first selection, in this section, the parameters that we will get are primarily they will not be used in single thing, rather they will be used to compare different models, whereas in this section we'll get the significance of our variables that we'll be using. Okay. So we'll go through individual things. So let us see how the model performs. And we have also calculated the residual error, square of error. Okay. This is again one thing that will be used to compare different models. The lower it is, the better it is. So let us quickly get rid of these things. Okay. Now let us talk about them one by one. Just a second. Yeah. First thing is log likelihood. It's an estimation of our most likelihood estimate. So again, as I mentioned earlier, we will be using this value to compare different models. The higher it is, the better it is. Like let's just scroll down to our next model. You will just get an idea of it. As the model improves, this value will also improve. See, it improved from 122 to 124. Correct? And it will keep on increasing once your model starts getting better. Okay. So the next thing would be I will talk about this one, AIC or Archaic Information Criteria. Is somewhat like it penalizes your model. The more number of variable you take, it will penalize your model the harder. The Bayesian information criteria also works like the AIC, Archaic Information Criteria, but it takes into account one more parameter, that is the number of rows. Okay, and at last we have Hanan Queen information criteria. This also works like AIC and BIC, but it's not used that much. Okay, so we'll try to reduce this value in our later models, but even if it does not, we can go ahead with other parameters also. We'll have to see which are means where in which model most of these parameter or criteria will satisfy our need. So let us go to our next section now. So in the next section, in this section rather, right, they have given us our variables used in this model, like AR L1 means autoregressive lag 1 and the passenger, and autoregressive lag 2 and the passenger, because if you remember we have selected our P as 2. So we have two lags over here. Okay. The coefficient is how it is affecting our model. Okay. The standard error, as we know, is if I have to talk about the formula, is the variance of the sample mean is equals to the variance of the population by the root over n, the number of observations. Z is this one, coefficient by standard error. Okay, and let me just quickly check. So we have 0.0096, and that is divided by 0.009, and you got something like 1.0648. Okay, almost similar to what we have. So let's do one more. 0.2359, sorry, 359 divided by 0.083. So say 2.8421, it is 2.855. Okay, fine. So it is almost similar. So this coefficient divided by standard error is a Z, this score. And this one, probability of Z score, this is very important. This gives us the significance of this variable. So by our criteria, these values should be lesser than equals to 0.05. Okay, so you could see that for both the variables it is less than 0.05. Okay, so you can conclude that both the variables are significantly contributing to our model. Correct. So to sum up, you will be using these few criteria in our in analyzing which model is performing better. First, we'll see this one log likelihood. We'll try and increase this value with every model. Okay. We'll also keep in mind the significance of each variable which are contributing to this model, and we'll also try to reduce this error value. Okay, so these are the three criteria that we'll keep in mind, and we'll move ahead with this one. And of course, the last thing will be we'll plot our actual with the predicted or forecasted value, and we'll see the difference. If it does not fit well, we'll have to go to some other model. So now moving on to our next model, we'll be using moving average model. So as we have seen in our earlier model, we have kept P at 2 and Q at 0. So in this case, we'll be making P value the order of autoregression model at 0, and our moving average model at 2. So this model will now necessarily become a moving average model, and using this model, we'll try and predict the values. So after that, we have stored the result in results.ma, and we have called the summary report. So let us take some time out to understand the report generated and how does it differ from our previous results. Okay. So let me just quickly scroll down. Okay, fine. Just a minute. I'll get rid of these markings. Okay. So as we have discussed earlier, we can see that the log likelihood measures have increased to 124, which is good. Similarly, these three criteria have also increased. It is also good. So this model is performing better than the previous model. Okay. If we try and understand the variables, there are two variables that are created because we have selected the order at 2, and they are more or less significant, though they are not completely lesser than 0.05, but they are close to 0.05. Okay. So we can conclude that this model is performing better than the previous model, and that is also supported by the our result of the squared error, which have also decreased to 1.4 from the previous one, which was let me just scroll up 1.5. Okay. So now we can conclude that moving average model is performing better than the autoregressive model, but we'll just have to check with other models how they are also performing. So we'll be doing that in the later section. Okay. So in this section, we'll get the predictions, and we'll also see, we'll plot the actual against the prediction, and we'll see how our model performed. So in order to do so, we'll first get our prediction result, and we'll be using our ARIMA model. Okay. So, but we have to keep in mind that whatever we have done on a log transform dataset. So we'll have to get that dataset back to our normal scale to actually see the result. Okay. In order to do so, what we have done is that after the predictions are done, we have found out the cumulative sum, then we have added it back to our ARIMA or log ARIMA model, and then finally we have taken an exponential of this prediction value to get the actual normal scale. Okay, so it is over here. We've taken the exponential. Okay, and then we are getting this result which is similar to our actual data set, the 112 actual number of passages. Okay, so let us create a data frame where we will have the actual predicted and the error. Correct. Okay, first let me get rid of this matrix. Okay, so let us scroll down. So this is the data set that I created. It will have the actuals, it will have the predicted, which we have predicted using the ARIMA model, the residuals actual minus predicted, and the residual square to get rid of the negative sign. Okay, and we'll further try and find out the root mean square of the error. Okay, so let us see that. So this is it. The second again. So what we have over here is that this is our actual data set that we have imported. This is our predicted data set that we have predicted using the ARIMA model. So this is the actual minus predicted residuals, and this is the residual square. So now we'll see the root mean square of this model. So the root mean square of this model is 90.1041. So again, a good value, and we'll have to compare it with other models to see whose root mean square error is less. But obviously, since this model has all the base parameters, this will be actually the lowest root mean square error. So let us do a quick plot to see how our model has performed. Now let us see. This is our actual data set, the blue ones, correct? And this is our predicted values. So we can see that our predictions was able to capture the trend, what the trends, okay? It was able to capture the fluctuation period wise, like up and down movement we could see. But one thing it has failed to do is to capture the seasonality. This seasonal pattern are not there in our predicted data set. This is because we have not taken into consideration any seasonality in our model. Okay, so see, actually, and one more thing, somewhat due to this non-seasonality present in our data set, or whether we are unable to capture seasonality, our predicted values are somewhere at showing some lower value than the actual value. Correct. So, for example, say let us say this one, say 1956, the 6 months, maybe 6 7 months. See, the predicted one is this one, whereas the actual value is around 400 plus, whereas our predicted peak is around 200. So now let us understand. We were able to capture the trend. We were able to capture the fluctuation. Means like we were able to predict when our demand will rise or go down. But what we are unable to do is that take our prediction close to the actual set. Like this, suppose we are planning our fleet operation in 1957. For this period, we are actually predicting a demand of only around 200. Okay, whereas the actual demand is around 400. So almost we are half. We are able to predict half will be the actual demand is. So from the business point of view, we might be underprepared in this situation. Though we know the demand will increase in this period, we don't know how much it is increasing, or even if we are able to predict how much it will increase, we are predicting quite a deficit amount than the actual one. So perhaps we need to work on this model a little bit more. So the first thing, let us include this seasonality in our prediction. First thing that we will do, and we'll also see if we are using a much stationary data set, what will be the results like. Okay, but before moving ahead, let us also predict using this our forecast that in next 10 years using our model. Although that is not that significant, but let us see what we get. So you have forecasted it using for the next 10 years using this ARIMA model, and let us have a look at the plot of it. So this is our prediction. Okay. So over here, this section is our actual data set, and this section is our forecasted data set. Correct. Again, we have got the trend. We've captured the trend. We know that it will increase, but unfortunately, no seasonality, no like fluctuation in demand. We are unable to capture anything. It's just a trend. Like it will go up. So that does not say much about our uh, deliver of the model. Okay, so as decided earlier, let us go for the seasonality induced model. Let's see what all we can do extra on this. So moving ahead, we will be using a model called SARIMAX model to correct our previous model, ARIMA model, in terms of seasonality, and we'll again do the same thing, like we'll predict using this model result and do the forecasting based on this model result. Okay. So first thing first, we will just call our SARIMAX function. So the extra thing that we need to do in this part is that apart from our ARIMA functions like 2, 1, 2, P, D, Q, we were also passing monthly the period value, the seasonal values. Okay, that is this one 12. So let us see what happens after doing that. We'll just quickly go through the result and see whether it fits our criteria or not. Testing log likelihood has gone down. AIC, BIC have increased. So these things are not falling in line with our criteria. Okay, now let us talk about the let us see the variables and how much they're significant. Okay, so let us see. Again, autoregressive lag 1, lag 2, MA lag 1, lag 2, and this is like autoregressive, seasonal, all the periods, 12 periods. MA, moving average, seasonal, all the 12 periods. So what we can see is that not significant, way higher than 0.05. Again, this one is also way higher than 0.5. MA L1 is significantly closer to 0.05, lesser than 0.05. And both the seasonal components, which is our main function, these two variables are extremely have become extremely significant now. Okay, so let's go ahead and see. Since our main objective is to induce these two seasonal factors in our model significantly, we were able to do so. Now let us go ahead and see what are the predictions, the error, and the plots look like now. So now you can see the actual result. Let us see. So this green line are the actual passenger data set, and the forecast one and the predicted values are the orange line. Okay. So now we can see that this model has the capacity of capturing this change, seasonality, and our actual data set of the or can replicate this one very closely. So we can say that our models perform very well. Okay. This with certain variables which were unable to make significant marks. But we could see that this is a very tight and close fit. So the model is performing pretty well. Now let us see if we forecast what happens to this we made. This is again that data frame that I created to show to give you a visual comparison. Like this is the actual one, and since we're taking a lag, we'll be operating it in the next part. So the residuals are almost same, and we've taken a square. Okay. So again, welcome to this graph. This is just a visual confirmation of how both the models ARIMA and SARIMAX are performing. So if you take some time out, this was the result of our SARIMA model, where we were able to capture the train, the fluctuation in our data set, but we're unable to capture the seasonality, as well as we are just under predicting ourselves. And when we have used forecasting based on SARIMAX, the orange line, it has perfectly fitted the actual data set. It was able to capture the train, the seasonality, as well as fitted our model pretty closely. Okay, so this is the visual confirmation of both the model and how they are performing. So now let us just see how our forecasting for the next 10 period have worked and whether it was able to make any significant contribution to our business. So in this section, we have used the predict function to predict the next 10 years. Next 10 years, that is the TF length plus 120, like 12 months, 10 months into 12 periods, 120. We've got these predictions. Now we'll just plot it along with our actual data set. We'll see how it has worked perfect. So let us see. If you talk about this section, sorry, if we talk about this section, this is our actual data set which had let me just try it a bit properly. So if we talk about this part, this was our actual data set, and this part is our forecasted data set for the next 10 period or next 10 years, correct? So now if we just draw a straight line, we'll see that this is able to capture the similar trend that we already have. Okay, so plus for our forecasted, our model were able to capture the similar trend that we are having. Correct. You see this one, similar seasonality. Sorry, not trend. We're able to capture it exactly. Fine. And both the data set, like the actual one and the forecasted one, looks like it is a continuation of the previous one. There is nothing absurd about this. So even if there is like from the business point of view, talk about say from 1948 to 1972, we're able to deduce graph or scenario where until and unless there are some major factors affecting our business model, major factors like the pandemics that we are in or the globalization and stuff like that, if everything goes right, our business will follow the same trend and will go ahead. Okay? So following this measure, we can plan out our future actions like fleets, fare, and operational matrices. So yeah, that's fine. So overall, what we can conclude over here is that a couple of things. Data set should be approximately stationary. Okay. If there is seasonality in your dataset, we'll have to go for a seasonal ARIMA so as to capture the seasonal variation. And if we are able to capture the seasonality, trend, and the cyclicity, if any, we'll be able to forecast correctly the future events. Okay, and plan our business according. So that would be it. Thank you for watching this session, and looking forward to interact with you again maybe sometime soon. Thank you very much.